Then we go to the last speaker of this block, which is Carsten Reekers. Carsten has a diploma in civil engineering and in business administration. He's working on the development and construction of underground gas storage and infrastructure. And he is a head of the underground storage operation at the historic Etzel project and a manager for the H2Cast R&D project. And I think you're going to tell us more about that project.
Yeah, thank you very much for the introduction. Maybe I need the remote control first. Right. Do we have the remote control for the... Ah, here. Okay, fine. So I want to give you a brief introduction our, let's say, applied science research project H2Cast. So H2Cast means H2 Cavern storage transition. So our scope of our project is to use to convert existing caverns which are formerly used for oil and gas storage and to convert them into hydrogen storage, and to test of highly flexible operating modes of these caverns for hydrogen operation. So this is a joint project together with our partner. So it's divided and it's split into two parts. So one part is the underground storage part, and the other part is the above ground facility part. So our scope is the underground storage part, and for the above ground facilities we have our partners with Gas Uni and with our other, let's say, partners Hartmann, Deutsches Zentrum für Luft- und Raumfahrttechnik, DEEP, and the University of Clausthal and SOCON. We have already started the project in 22, and we are, let's say, still ongoing into planning and start with the construction. But first of all, I want to show you the Etzel Cavern field, because this is very important. We talked about the infrastructure. So the Etzel Cavern field is very close to the deepwater harbor Wilhelmshaven. It's about 20 kilometers from Wilhelmshaven. We are already connected to the pipeline grid, to the natural gas pipeline grid, to the Netra and the Bunde Etzel pipeline, to the Netherlands border. And as well, we have pipeline connections with for brine and seawater from Wilhelmshaven, which is very important for leaching the caverns and as well for our project, which I will explain. So the infrastructure in the northern German region is already existent. We are only, let's say, waiting for hydrogen, and that was our reason, because we would not like to wait until we get the pipeline infrastructure for hydrogen. We would like to start our project to get the caverns H2 ready. Today we have already 75 caverns in operation. 24 caverns are in operation for oil, for the strategic oil reserves, and another 51 caverns are in gas operation. And we heard about what is about energy safety. So the Etzel Cavern field was founded in the early 70s. The reason was because of the oil crisis in Europe and in Germany. That was the reason, because the federal state of Germany was, let's say, established underground storage for crude oil reserves. So that was, let's say, the nucleus of the Etzel Cavern field. And then what we did in the past, then in the, let's say, in the beginning of the 90s and 20s, it started, let's say, the natural gas grid development in Europe. And then we have already converted a couple of caverns which were formerly used for oil storage into natural gas storage. So, and these caverns are still in operations more than 15 years. And today we have about 11 caverns which are in the leaching process, which we can use for our H2Cast project. Altogether, we have about 99 locations for caverns which could be brought into operation, so we have all the permits to do this. Yeah, you can see it's a picture of the subsurface ground. It's made from the sonar control, from the sonar surveying, and these two caverns. So this is all the caverns which are already existing and part of them in operation. We have gas caverns and we have oil caverns. And you see on the surface we have these clusters where all the wells are to be bundled to make the infrastructure easier to connect them with the grid. And two of these caverns we have separated from the process. It's a cavern which in a leaching condition, which were designed for natural gas storage, which we take into the project of H2Cast. So we have not to build a new cavern for our project. We use already existing caverns. Yeah, the scope of our H2Cast project is, of course, evidence of tightness of salt rock and as well as a completion. And the proof of the material we have just heard, this is very important. The question is, can we use the existing material which is in operation for natural gas? Can we use this material already for hydrogen operation? So this is a big question. That means the pucker, the tubing casing, cementation, and the subsurface safety valve, the wellhead, inclusive valves, and so on. This is a very interesting and important question, because some of the installation, for example, the casing and the cementation is already there. So we would not like to remove it. So we would like to use it, and we have to take the evidence that will be proper work. As well, of course, the rock mechanics, the salt characteristic, H2 permeability. We heard it this morning. We do some samples with the existing drill cores from the wells which we still have, and the cavern convergence due to a multi-cyclic operation. On the other hand, it is very important for the market, the H2 purification, because we use former used oil caverns or natural gas design caverns which are leached with crude oil as blanket to protect the cavern roof. So all the caverns are contaminated with higher carbons which are coming from crude oil. So we want to show that we can use this cavern and we can purify the withdrawal hydrogen from the higher carbons. And of course, we want to understand the process of purification of hydrogen, and let's say the cost, the technique, and the energy consumption of the facilities. For the hydrogen market, we are coming from a seasonal natural gas market. That means in the winter period we inject natural gas in the caverns. In the summer period we will inject. In the winter period we will withdraw natural gas. And for a hydrogen operation, we think it's something like a multi-cyclic operation. So it means a high pressure drag vent from day to day. It's not a seasonal, so it's a multi-cyclic operation that we also would like to test in our project. And of course, the guidance of approvals, in particular the mining law in Germany and the Major Accident Acts. So today we on a step that we get all the permits we need to go forward. But we had to do a lot of things with material investigations and so on to get the approvals. And of course, the influence on H2 quality, we heard it, and I think tomorrow Nicole will also tell us something about H2S, and because we have higher carbons and lower carbons in the cavern. Plant maintenance, of course, this is a very important thing, because we have to do all the, let's say, plant maintenance and tests and checks for well integrity under pressure hydrogen conditions. And it's very difficult to get service companies which are allowed to work under hydrogen conditions, because hydrogen is a little bit different from what we know from natural gas. And as well, the market availability of the components we have just heard. For example, we have heard something about safety valve and something about puckers, so on. For example, for our H2Cast project, we have redesigned a former used subsurface safety valve, which was already installed in the natural gas cavern, and we moved it out and we have redressed it, and we will install it in the hydrogen cavern, because it's all the same materials that we use for natural gas, so there isn't any change. So we built some new threads on it, hydrogen gas tight threads, and we will reuse it. So we won't buy new one, because anyways on the market there aren't any components for underground storage available which are especially designed or, let's say, certified for hydrogen. So you have to use the materials which you already get on the market. Otherwise you have to wait a couple of years, because there's worldwide not such a big market that, let's say, the huge suppliers of this special equipment are very interested to bring, let's say, the market design forward. And as well, the system integration, gas, electricity grid, for example, and the gas grid. This is part of the Deutsches Zentrum für Luft- und Raumfahrttechnik. As well, the economics are very important, because we would not like to build new caverns. We want to redress and use the existing caverns. So therefore, it is very important that we know about the costs for converting the caverns. And the idea of our project, this is a sketch of our H2Cast. So we took two caverns, and the question we asked in the beginning was, because if you would like to store hydrogen in caverns, you need huge amount of hydrogen. But the problem was there isn't any hydrogen on the market, and there isn't any grid for hydrogen transportation today. So then we came to a conclusion what we can do to start now and not to wait until the grid is ready to get this high amount of hydrogen. And then the idea came up, we use 2 caverns, and so then we can cycle the hydrogen from one cavern into the other cavern. So that is the idea. That means the second cavern, this is this one without any completion, I explain this later, is like something like for the demand on hydrogen and let's say for the production of hydrogen. So on the right side we see a typical completed gas cavern with a pucker installation, with a subsurface safety valve installation, but anyways the size of the cavern is close to 200,000 cubic meters. That means that we need a couple of thousand tons of hydrogen to fill it, and of course this will take years and will cost a lot of money. And therefore we came to a conclusion that we only fill the first part of the roof of the hydrogen. Therefore we need about 80 tons, that is more or less 1 million standard cubic meters of hydrogen. For example, a complete cavern has a capacity of 100 million cubic meters of hydrogen. So we only need about 1% of the hydrogen of a later hydrogen operation cavern. And what is required for this, we have to level the working gas volume of the hydrogen cavern while inject with high pressure and withdrawal brine. So then we can, let's say we can adapt the working gas volume of the caverns due to our existing leaching facilities. So it's quite easy. So we will pump brine with high pressure, which we have in the cavern field, and we can, let's say, withdraw hydrogen and pump it via a compressor into the other cavern. And therefore we can cycling, and due to we can adjust the hydrogen brine level, it is possible to reduce it, and then it is also possible to, for example, produce high pressure gradients to simulate a multicyclic cavern operation. And all the tests which are required we can do the same way on a typical, let's say, standard cavern, because the most interesting questions are here at that area. That is, for example, the cementation of the casing shoe, the material test of materials, and the well integrity at the roof of the cavern and the borehole itself. So all these tests could be done and checked in situ with hydrogen without filling a complete cavern with hydrogen. So this is a project idea, and to see where we are. So this is the Etzel storage facilities. We are here in the center of the facilities. All around here we have the compressor stations for natural gas, and in the north fields, it's about 3 kilometers, we have this cavern clusters. And 2 of these caverns, this one and this one, are designed and now in operation to convert it into hydrogen. So we are using all the existing facilities we have. We are using the pipeline grid for brine and for seawater, which we need to leach the caverns, which we need to produce brine to adjust the working gas volume. This is the actual draw of the design of the brine balancing system. So we have, this is a cluster, cavern cluster. We have our 2 caverns, and this is our high pressure leaching facilities where we can inject brine, which we get from the field pipeline system from the other existing caverns. And the 2 caverns will be connected via above ground facility each other, and then we can, let's say, cumulate hydrogen and brine between those both caverns. Yeah, what we already did is a pre-tightness test. So you can see on the right hand side, this is a typical assembly for a tightness test. We have to inject hydrogen into the cavern roof, and then we test and we measure the brine hydrogen level and the temperature and some other data to calculate the figures of tightness of the caverns. The idea was for this pre-test to do this pre-test for the substance H2 installation to start with a pretest, to know how it works, to know that in principle the cavern is tight and the materials will be work for our H2Cast. But on the other hand, our task was to get more experience in handling with hydrogen and hydrogen operation, training our staff and risk assessments. Because in this way, if we start to do a high pressure test with hydrogen, we do have to do all the, let's say, risk assessments and so on to go forward with it. And of course, we have done a lot of material assessments of the existing wellhead. That was very interesting because we haven't installed anything new. We used 30 years old existing leaching wellhead with old materials which we tested, and we get the approval that we can use it also for hydrogen. So the 30-year-old material was suitable for hydrogen. And the procedure was quite easy. So we have inject hydrogen by a trailer with 300 bar. About 280 kilo, and then we had a test pressure with 138 bar. This was the maximum allowed pressure for the wellhead at this time, and we do several measurements from November to January this year. So the findings are that the tightness was approved, inclusive the old leaching head. We have the compatibility with the results from previous more than 30 tests of natural gas caverns. So we did the test first with nitrogen and then with hydrogen, and we have compared the results, and then we have compared the results with other test results from more than 30 caverns which we developed in the last decade, and let's say the findings were quite similar to the tests we had before. So, or I put it like this: that we can't see any difference from all the other tests in the last decade of years. And on the end of the test, we had to do some operation with H2. We have to vent and to flare the hydrogen. So this is a plot of the cavern. So what we see is this is one of the caverns. The other one is in the background we can't see. So here's a hydrogen truck which we had. This is Socon for the sauna control. So we injected the hydrogen. It took about only 3 hours. It was much easier than we expected before. And then the whole test took about 3 months to do from time to time several measurements to calculate the amount of hydrogen which is still in the well to approve the tightness. And what we have seen here, this was something for emergency. If we need, let's say, a high pressure drop, a release of hydrogen, we can, let's say, pump it or bring it into a filled water tank and a flare which we have built for this. Just in any case to get a quick release of hydrogen. Maybe in the break I have also a film, because in the end of the test we have to flare the hydrogen. I have a film which takes about 1.5 minutes. It can show how we ignite the hydrogen, how it burns. It was very surprising because it was very difficult to ignite it. So everybody was asking if we took this into a test preparation, that maybe hydrogen ignite itself. And then was my answer, okay, if you think it will ignite itself, then we have to check it. And if not, we will ignite it, because then we know, then we see what will it brings. Because if you have all the facilities and you are thinking maybe it could be ignite, then you have to make sure if it is so like this, then you have to test it, and that's why we always test it for this. I put it in the coffee break. It's very interesting. And as well in the parallel time, we did a lot of material investigation. Not we have another university with material science who have done this for us, and the results are quite easy. So the lower carbon steels isn't any question, but we tested the higher carbon steels. For example, for the packers, for the safety valve, we have some high strength yield steels, and they could have an impact with hydrogen influence. And we also tested the maximum load of hydrogen in the steel, because you can only have a hydrogen risk enforced embrittlement if the hydrogen will get into the structure of the steel. And there were also some very interesting results of it. So the efficient hydrogen in the material was quite less than what we expected and what we can see in the literature. And we did, of course, a lot of vectographic investigations of the samples. Then also some constant load tests with hydrogen environment. And this was very interesting. All the materials we tested, we used it from existing wells. The same materials which were installed a couple of years, 10 years more or less, in other wells. For example, we tested wells, existing wells with typical materials under hydrogen atmosphere. For example, we tested the hangar of the cavern. This is a part where the maximum load is in the cavern completion. And as well, maybe anybody knows what this is here. It's a spring, and this is very important. It's a spring from a subsurface safety valve. I think never had tested it before because we dismantled one of the safety valves and put all the pieces into the laboratory and tested with hydrogen because the supplier of the materials can't give us any, let's say, guarantee that will be works. Then we thought, when we come to the conclusion, we have to do it on ourselves to test it, to go forward with it. Yeah, that's it. A brief summary of our project. And in September this year, we start with a cavern completion. It's already scheduled, so the material is in place, the services are in place, and we start with a high pressure test to the maximum allowed pressure of the rock mechanic, which is close to 180 bar more or less, end of this year. And we start to fill the first cavern with hydrogen in the middle of next year.
Fantastic, thank you very much. While we take questions, we forgot to also give gifts to our speakers. Previous Evan is there, and then Bert. Where are you? Bert is there as well. So Serge will help me with the gifts, and I take the questions. Ian, and then we have two. Who else? Questions. We encourage those who have not yet asked questions. So Sam goes first, and then Ian, you have asked.
Hi, great. Thanks very much. Sam Crever from Imperial College. I was just wondering, looking at some of the schematics here and then from the earlier presentation about the caverns in the UK, why is wet storage not more widely used as a typical storage mode? So the storage with essentially filling the cavern with water as you deplete the cavern of hydrogen. It seems that it helps to deal with the pressure cycling, it helps to deal with the issue of cushion gas, but I'm assuming there are some issues. I'm just wondering what those issues are.
Yeah, so the idea was because the lack of hydrogen, so we haven't enough hydrogen to get the cavern filled. So that was the reason why we use brine-filled caverns, where we will only inject the hydrogen in the roof of the cavern itself. It was only the reason why we have to, let's say, transport it via trucks. And I've calculated it, we need 150 trucks for hydrogen injection. And only for our test, it was very interesting. We bought green hydrogen, and then it was very difficult only for this test to get the hydrogen. First it was coming from Frankfurt, then let's say the facilities were out of order, then it came from Innsbruck. Via truck from Innsbruck to northern of Germany only to get 300 kilos of hydrogen. So it was crazy. So the idea is just, but with a cavern with a filled in the top of the cavern in the roof, so we can do all the tests which are required to get evidence of the suitability of the cavern. I'm personally I'm convinced that it will be work, and there aren't any material changes required for convert caverns from natural gas to hydrogen. That's my opinion.
Thank you very much, Hein van Gent, State Supervision of Mines. The Etzel field is quite an extensive field, as you've shown, with many caverns. Can you comment on the monitoring that you have in place for cavern stability and maybe subsidence, and how you, and maybe gas detection as well, leakage detection, and what kind of changes you will implement when this field gets partially converted to hydrogen storage?
First, regarding the subsidence, the whole cavern field is under a monitoring program. We have about more than 300 measure points for the subsidence to check the subsidence. These measurements will be taken yearly, and we are now investigating in radar interferometry, so to get it from the satellite assistance to get more numbers, figures of subsidence. The cavern itself monitored, so all the data of the cavern, the pressure, the temperature, the flow rates, monitored from our processing system into a database, and will be stored permanently. So I can look in every well 10 years in the past and can look what if there is anything which could be quite different from, could be not normal. So this is very interesting. This is let's say the whole well integrity works with storing of all the data from all the transmitters. Every 3 seconds we get one figure from the well monitoring for all the caverns. So thousands of numbers. And you can look in the well control monitoring system, for example, for the annulus control system, is there any activities? We have other wells to check if there are any gases in the soil. And so we're collecting all the data, and we can look in the past, and just in any case, if there's anything which could be quite different from the normal operation.
Thank you very much. So in view of time, we move on, and let's thank Carsten one more time. Thank you very much for this excellent presentation.